We're diving into how well a logistic regression model predicts probabilities. A perfectly calibrated model means its probability predictions accurately reflect the real-world chances of an event happening. Think of it like this. If the model predicts a 70% chance of rain, it should rain about 70% of the time when that prediction is made. I'll be testing your understanding of model calibration in this multiple-choice question. Get ready to apply what you know about calibrated models and how to improve them. I'm giving you a scenario. You built a model, logistic regression, using the popular Sklearn library. It's performing great on training data, 90% accurate, but flops on new data, 70% accurate. This gap points to a problem called poor calibration. The model's probability predictions aren't reliable. A well-calibrated model's predictions match reality. If the model says something has an 80% chance of happening, it should happen around 80% of the time. Flat scaling is a technique to fix poorly calibrated models. It tweaks the model's probability predictions by fitting a special S-shaped curve, sigmoid function, to them, making them more accurate. Isotonic regression is another way to improve calibration. It's flexible and doesn't assume any specific shape for the relationship between predicted and true probabilities. However, it can be sensitive to small datasets, potentially learning the noise in the data rather than the underlying pattern. Calibration curves are graphs showing how well calibrated a model is. You plot the predicted probabilities against the actual frequencies. A perfect model would lie on a diagonal line. Predicted probabilities exactly match the observed rates. Choose all the correct statements from the options given. I'm looking at a situation where we're using logistic regression, a type of model that predicts probabilities, to classify things into two groups. We're trying to make sure our model's predicted probabilities are reliable, meaning they accurately reflect the real-world chances of an event happening. This is called calibration. We have a model that's doing great on the data it was trained on, accuracy, but it performs poorly on new data, accuracy. This suggests the model might be overfitting, learning the training data too well, and not generalizing to new data. We are looking at if the model's probability predictions are trustworthy, and this is called poor calibration. Flat scaling is a technique that takes the model's initial probability predictions and tweaks them using a sigmoid function, a curve that transforms numbers into probabilities, between 0 and 1. This adjustment aims to improve the reliability of the probabilities. Think of it as fine-tuning the model's predictions to better match the real-world frequencies. Isotonic regression is another method to calibrate probabilities. It doesn't make assumptions about the shape of the relationship between predicted probabilities and true probabilities. That's what non-parametric means. However, because it's flexible, it can sometimes overfit, meaning it learns the training data too well, and it might not work as well on new data, especially if you don't have a lot of data. Calibration curves, also known as reliability diagrams, help visualize how well calibrated a model is. They plot the predicted probabilities against the actual observed frequencies. A perfectly calibrated model would lie along a straight diagonal line, indicating that predictions match the observed data perfectly. Deviations from this line show where the model is poorly calibrated. A well-calibrated model's predicted probabilities should align with the actual outcomes. For example, if the model predicts a probability of 0.8 for an event, then, in a large number of similar instances, roughly 80% of those should actually be true positives. That is an example of a well-calibrated model. I'm focusing on how well a logistic regression model's predicted probabilities match the actual outcomes. It's about how accurately the model's predictions reflect reality. Think of it like this. If I predict an 80% chance of rain, and it rains 8 out of 10 times when I make that prediction, my model is well calibrated. If it only rains 2 out of 10 times despite my 80% prediction, it's poorly calibrated. Flat scaling is a technique I use to adjust a model's probability predictions. I do this by fitting a special S-shaped curve, a sigmoid function, to the original predictions. This curve helps to improve the agreement between predicted probabilities and actual outcomes, making the model better calibrated. It's a bit like fine-tuning the model's probability output to be more accurate. Isotonic regression is another way to improve calibration. It's flexible and doesn't make strong assumptions about the data's shape. However, with limited data, it can be prone to overfitting, meaning it might learn the training data too well, performing poorly on new data. It's like fitting a curve perfectly to a small set of points, but that curve might not be a good representation of the bigger picture. Calibration curves, also called reliability diagrams, are visual tools I use to check how well calibrated a model is. I plot predicted probabilities against the actual observed frequencies. A perfect model would produce a straight diagonal line because the predicted probabilities exactly match the actual outcomes. Any deviation from this line indicates some degree of miscalibration. A well-calibrated model means that there's a good match between what the model predicts and what actually happens. If the model says there's an 80% chance of something, you expect it to happen around 80% of the time. It's all about the model's predictions aligning with reality. This is the core idea behind calibration. All statements A, B, C, and D are correct descriptions of important concepts in model calibration. I'm focusing on how well a logistic regression model predicts probabilities. A well-calibrated model means its predictions accurately reflect the real chances of something happening. For example, if the model says there's an 80% chance of rain, it should rain about 80% of the time when the model makes that prediction. That's what we want. The question highlights a common machine learning problem. My model is doing great on the data it's trained on, 90% accuracy, but performs much worse on new, unseen data, only 70% accurate. This suggests that my model may be overfitting the training data. Therefore, I need to investigate the calibration of my model's predicted probabilities. Calibration is about how well predicted probabilities match the actual outcomes. A well-calibrated model's predictions match reality. If the model predicts rain with 80% probability 100 times, it should actually rain around 80 times. This is the core of calibration. Platt scaling is a technique to improve the model's probability predictions. It tweaks the probabilities using a sigmoid function, a special S-shaped curve, to get better agreement between the model's prediction and the actual outcome. Isotonic regression is another method that helps to calibrate. Unlike Platt scaling, it is non-parametric, meaning it doesn't assume a specific shape of the relationship between predictions and actual outcomes. However, because of this flexibility, it is sensitive to noise in smaller datasets and might overfit. That means it might do really well on the training data but poorly on the test data. Calibration curves are graphs that show how well my model's predicted probabilities line up with the actual results. A perfect model shows a diagonal line, showing a perfect match. If the line deviates, it tells me how and where my model is miscalibrated. This is asking you to identify all the true statements about model calibration from the previous options, to assess your understanding of calibration methods and visualization techniques. I'm presenting a scenario about a logistic regression model. The model's accuracy is great on the training data, 90%, but it's much lower on the testing data, 70%. This suggests a problem with calibration. The model's predicted probabilities might not accurately reflect the true probabilities. The question is designed to see if you understand what model calibration is and how we can improve it. I'm explaining the meaning of a well-calibrated model. It means the probabilities a model outputs should match what actually happens. If it predicts an event with probability 0.8 out of 100 times, roughly 80 times the event should actually occur. That's the gold standard for calibration. I'm introducing Platt scaling, a technique that directly adjusts a model's probability predictions. It does this by fitting a sigmoid function, an S-shaped curve, to those probabilities. This helps improve calibration. I'm explaining isotonic regression, another calibration method. Non-parametric means it doesn't assume the data follows a specific distribution. It's really flexible, but with limited data, it can learn the noise and overfit. I'm describing calibration curves or reliability diagrams, which help us visualize how well calibrated a model is. We plot predicted probabilities against the actual observed frequencies. A perfect model shows a diagonal line. Points away from the diagonal mean less perfect calibration. This section sets the stage for the quiz. We will evaluate calibration in a binary classification problem. 2 classes, using logistic regression with scikit-learn. This is the instruction for answering the quiz question. You need to select all the true statements about model calibration. We're tackling a problem where a logistic regression model, a type of statistical model used for binary classification, isn't performing as well as expected. We'll examine how well the model's predicted probabilities align with the actual outcomes. Think of it like this. If the model predicts a 90% chance of rain, and it rains 90% of the time when it makes that prediction, then it's well calibrated. I'll be evaluating your understanding of concepts related to calibration. This is a multiple-choice question testing your understanding of model calibration within Sklearn. You will pick from multiple options. I've trained a model, and it performs great on the data it was trained on, but poorly on unseen data. This suggests that the model might be overfitting or poorly calibrated. A well-calibrated model would ideally have similar accuracy on both training and test datasets. We need to evaluate the quality of its probability estimates. Flat scaling is a technique I can use to adjust the model's probability predictions. It involves fitting a sigmoid function, an S-shaped curve, to the existing probabilities, making them better aligned with the observed frequencies. This often improves calibration. Isotonic regression is another method I can use to calibrate the model. It's flexible, not relying on specific assumptions about the data's distribution, but it's sensitive to small datasets and prone to overfitting, meaning it learns the training data too well and doesn't generalize well to new data. Calibration curves, also known as reliability diagrams, provide a visual check of calibration. They plot predicted probabilities against actual frequencies. A perfectly calibrated model would show a straight diagonal line, indicating perfect agreement between predicted probabilities and observed results. This is a multiple-choice question testing your understanding of calibration in logistic regression models. It presents a scenario where training accuracy is high but test accuracy is low, a classic sign of overfitting and poor calibration. The question probes your knowledge of calibration concepts and methods to fix the issue. Let's dive in. Flat scaling is a calibration technique. I use a sigmoid function to transform the model's raw probability predictions into better calibrated probabilities. Think of it as a post-processing step that fine-tunes the model's output to make the probabilities more reliable. Isotonic regression is another calibration method. This method is non-parametric, meaning it doesn't assume any specific shape for the calibration curve. However, because of its flexibility, it runs the risk of overfitting to noisy data, especially if I have a small dataset. It's a powerful tool but needs careful consideration. Calibration curves, also known as reliability diagrams, provide a visual check of how well your model's predicted probabilities match the actual event frequencies. A perfect model would show a straight diagonal line, indicating a perfect match between predicted and observed. Deviations from the diagonal line show areas needing calibration. This statement defines what calibration means. A well-calibrated model's predicted probabilities should closely match the observed frequencies. For example, if the model predicts a probability of 0.8 for an event, about 80% of those events should actually happen. It's about the model's predictions being trustworthy. This refers to a specific calibration method mentioned in the question, which uses a sigmoid function to adjust predicted probabilities. This describes a visual tool, calibration curves, used to assess a classifier's calibration. They plot predicted probability against the observed frequency. This refers to another calibration method, a non-parametric approach that can be prone to overfitting on small datasets. This is simply the format of the question, it is multiple choice. This is the overall topic of the question and its options. It focuses on evaluating and improving the reliability of probability predictions from a logistic regression model.